folks. This is Professor Parks, PhD, and welcome back to the channel. Hope you all can hear me all right. I noticed when I was loading this up that my speakers weren't working, so I had to fix that. Hopefully that doesn't mean other settings have been, for mysterious reasons, futzed. So, Judy, if you cannot hear me, please let me know in the chat, and I will continue to see if I can fix it. Let me just make sure that the audio is mic, yes, speaker. I'm gonna go with that. We'll go with that. See what happens. All right. So, excuse me. Well, what are we going to talk about today? Well, I'm going to talk to you a little bit, or maybe a lot, about stellar interiors, and more specifically, actually, I'm going to talk about, not really, let me back off that. I'm not going to be talking about stellar interiors. I'm going to be talking about geologic activity, some of which stems from what's going on in the interior. But I'm not going to be going over the specifics of the interiors themselves. Anyway, so let's jump right in. Oops, that is not the one I want. Decided to take down my logo just for these lectures. Yeah, I'm pretty sure you all know who I am. So what is our goal with learning about planetary surfaces? Why do astronomers care about essentially the morphology or the characteristics of a planetary surface? Such as, why do we care about cratering? Why do we care about evidence of volcanism or tectonics or what have you? What we'll find is, as I've sort of alluded to, is that a number of these activities or a number of these effects are due to the internal physics of the planet. What essentially is going on underneath the surface is dictating what the surface itself looks like. So if we know what the surface looks like, we have a better understanding of what's going on beneath it in order to give rise to those observed features. Also, we can use stellar surfaces to these same features to determine the geologic age of the planet. More specifically, I'll be talking about impact craters, but really all of these apply. You can think of basically the frequency of all of these different phenomenon is going to play a role into figuring out what the geologic age is. Typically, if you have more volcanoes present, you can say that the geologic activity of that planet was probably longer than, say, a planet that has fewer of them. So in a way, we're going to be doing comparative planetology, one on the surface itself, but also comparing surfaces on one world to a surface on another world. And then at the very end, either this lecture or the next, depending on how things go, I will talk about why it is that we have of the 5 terrestrial worlds. Obviously, the Moon and Mercury look very, very similar, but Mars, Earth, and Venus looks markedly different. And Venus and Earth have very similar bulk characteristics, mass, radius, and density, yet look very, very different. And so I'm going to talk about the 3 reasons why that is. Excellent. I'm glad the sound is good. So, what are the processes which shape planetary surfaces? Well, I'm going to be talking about 4 in particular. First one is impact cratering. This is the impact of either an asteroid or a comet, something that has mass that is moving at a sufficiently high velocity. I could also say I could also put meteoroids into this equation, but really, I don't quite understand the difference between a meteoroid and an asteroid. I get what a meteor is. I get what a meteorite is, but I don't quite know the difference between a meteoroid and an asteroid. So I'm just going to simplify it down to asteroids and comets. Then you have volcanism, which typically represented through the violent action of molten lava, molten rock streaming out onto the surface. You also have tectonics, which is the shaping of the surface, either the compression or stretching of a planetary surface due to underlying motion in the mantle region underneath the lithosphere. You can also have, as I said last time, the Earth is the only world to have what we refer to as plate tectonics. Is that action, that mantle action, is so violent in comparison to the thickness of our lithosphere that the lithosphere is actually cracked into plates. And I'll talk a little bit more about that as well. And then finally, you have erosion, which is the changing of a surface feature due to wind action, ice, or water movement. So what about impact cratering? Impact cratering is probably the most dramatic feature of the moon. If you put a pair of binoculars or a small telescope on the moon, the first thing that really pops out to you are the impact craters, the pock marks all over the surface of the moon. And when you look at the moon naked eye, you can definitely see those gray stains, which I'll talk again a little bit more about in this lecture. But when you can only see the cratering when you can see it magnified. The craters themselves aren't big enough for us to see with our eyes. We actually need a small telescope. So what are these? What exactly, and what are these? How do they form? And what sorts of shapes and sizes can they come in? Well, from a basic perspective, what an impact crater is a detonation. So you might think naively that an impact crater is where something falls onto the ground and then digs out the surface like a divot, like basically a golf ball into a sand trap. That's not really what's going on here. What's going on is that impactor typically has a great deal of energy associated with it because of its motion, also because of its mass, but also because it typically has a very high velocity. Canonically, we say that the average is around 45 kilometers per second. So these carry quite a bit of kinetic energy, and when they hit, they will cause an explosion, and that explosion will blow out material, but it will also cause the impact site to become molten for a fairly short period of time. In addition to that, it will also send out seismic waves, which will also affect the features. So depending on the amount of energy, your impact crater can look very different. And so we have a number of different impact craters around that we see around the solar system. We see them on Earth. This is perhaps the most famous, or at least I think so, because this is the only one that I have actually been to. Howdy, Clive. Howdy, Nimrod. Well, I don't know about aliens, but if you watch certain movies, the space Nazis definitely hang out in craters on the moon. But this crater is Meteor Crater, or more properly known as Barringer Crater. The reason why it's more properly known as Barringer Crater is that this crater is actually privately owned. It actually, this crater or this impact happens to be on the land of Mr. Barringer, I guess, who owns a ranch, and he owns that particular land, and so he is now basically, if you go, you have to, in order to see the crater up close, you actually have to pay $20. This was actually about a decade or so ago, but I think it's worth it. And what I love about this crater, and the specifics are there, it's about 1.2 kilometers in diameter, about 170 meters deep, and we believe that it was a stony iron asteroid of about 50 meters in size that smacked into this. In terms of the devastation, the local devastation that this impact has, let me also say that this impact is only about 100,000 years old. So the thing that hit this thing happened only 100,000 years old. And again, I use the word only because we're talking about astronomical or geologic timescales. That's very recent. That's almost within the span of human existence. When you talk about the devastation that this impactor could have occurred, we're talking this is probably going to have affected the region about the size of the state of Arizona, maybe a little bit less. And I've got a nifty toy to kind of help illustrate those sorts of things that I'll show you later on. But this is Meteor Crater is an example of what we would refer to as a simple crater. It simply is a essentially bowl with a raised edge that is roughly circular. Now, the thing I love about this, the most memorable thing about Meteor Crater to me is actually not the crater itself, because, let's face it, it's a big hole in the ground. It doesn't really have a lot of striation in terms of geology, so it's not really all that pretty to look at, although it does have a little bit near the surface. But it's just basically a big hole in the ground. I mean, if that does it for you, no kink shaming here. But the thing that really was kind of just awesome for me was, as you're driving up to this place, and this place is in the middle of nowhere. It is a stark desert. It's very flat. There is no topography really much at all. And as you're approaching it, you start to see, really, I don't think I'm familiar with that. I'll have to look that up. I'm going to assume that that place has a lot more trees around it than Arizona, the one in Arizona does. But I'm going to Google that in a sec. When you're driving up, like I said, this place, Arizona, in this region of Arizona, it's a desert. It's very flat, very arid, really no topography whatsoever. And then as you're getting closer, you start seeing bigger and bigger boulders just hanging out, doing their thing. Like, there's really not a lot of rocks around them, and you can tell that they are, in fact, boulders and not protrusions coming up from underneath. And what these are, and as you get closer and closer, the boulders get larger and larger and a little bit more frequent. What these are secondary impactors. So when this thing popped off, when that impact happened and the explosion occurred, creating that crater, as I said, it blew out material. And that material will then rain down on the environment surrounding the crater and cause what we call secondary impacts or secondary craters. Now, as it happens, as with a lot of craters on the Earth, those secondary impact craters have been essentially worn away through erosion. But the impactors themselves managed to survive, or at least the larger impactors themselves managed to survive that secondary impact. I don't. Yes, I believe it is in fact also geometrically level. I will go out on that lane. All right, hold on a second. I can't spell, so I'm going to put this over here. There we go. Meteor. I can do this. Crater. Oh, that's weird. Hold on a second. So, Judy, are you talking about... That's not what I want. Over here. Let me stop screen. Let me share screen. Let me do that. We're talking about that. Is that the meteor crater? Because that's what I get when I Google it. Because if so, that's actually pretty awesome. Because basically it shows the evidence of erosion that has happened. Basically, Here, in this case, you have quite a lot of erosion, and the crater walls, which in this crater is, again, seems to be far larger than the Behringer crater. The walls are pretty much gone. So this must be a very, very old crater feature. So, and it looks now like it's being primarily used as farmland. So, which that doesn't surprise me. I imagine that the soil is quite rich in nutrients because of the impact. But hey, I'm not a farmer, so what do I know? Anyway, let's go back to this, and let's talk. Let's continue to talk about craters. So when we look at impact craters, Vasa, the water was pumped out decades ago. Wow, all right, cool. I'll look more into that. And so if we look at impact craters so again, let me take a step back. That the Behringer impact crater, and actually, thank you for showing me Soderfjorden. We're going to go with that. Soderfjorden. That crater is another example of craters that you find on Earth. I'm going to show you, I'm going to talk about an even larger example momentarily, but on most of the craters that we see on the Earth, and we can identify them as craters, they are what we basically refer to as simple craters. They're relatively small, only about 1 kilometer in size, and they're relatively bowl-shaped. If they're any larger than that, then the edges of them have been basically sandpapered down due to erosion, either rain or wind or both. So you really don't get to see any of these craters that we see on Mercury and the Moon. From smallest to largest, we actually have the simple crater is not the simplest crater. The simplest crater is what we refer to as a pit. And this is actually microscopic. These are caused from micron-sized or 1 to the 1/1,000,000th meter sized dust grains that smash into the Moon or Mercury. Now, obviously, with the Earth, this sort of stuff, it hits us. We refer to these as micrometeorites. That stuff hits the atmosphere, and most of it gets burnt up, and its constituent atoms get recombined with anything else. Anything a little bit larger than that actually will slowly fall onto the Earth as basically dust. About 50 tons of it, I think 50 tons of it a year, maybe 50 tons of it a day. I think it's 50 tons a day rain down on the surface of the entire Earth. While that sounds like a lot, if you imagine the surface area of the Earth, it's why we don't see it just raining down from the sky. Anyway, and so those are what we call pits. So microscopic divots or microscopic cratering. Those we refer to as pits. Then you get to simple craters, which range in size all the way up to 1 kilometer. For the Earth, anything that is lower than that, 1 kilometer, or basically on the order of less than 1 kilometer, depending on when it formed, it's more than likely going to have been completely destroyed due to erosion. Then, again, going back to Mars and Mercury and the Moon, the next thing up is you have a complex crater. Now, if any of you have ever seen, for some reason this always sticks in my mind, maybe because I just don't like milk, but I remember kind of a slow motion picture of a milk droplet falling into a glass of milk. And if you've ever seen that or something similar to that, it'll hit the surface. The surface will bow out, basically create something akin to a crater, and then it will rebound and spike in the center of it. In a very analogous way, that's essentially how complex craters are formed, is that now you have an impactor that is carrying more kinetic energy than one that would form a simple crater, and that kinetic energy is sufficiently large enough to cause that explosion, and the crater becomes, or excuse me, the bottom becomes molten. There is a significant amount of seismic activity that stretches out, and the energy is held longer so that the material stays molten for longer. And as it rebounds, it forms this small little mountain in the center of it before the whole thing freezes over and gets frozen. Thing you may notice between the complex crater and the simple crater is the simple crater has a very simple, very well-defined rim. Whereas a complex crater, you can see that there are kind of ridges in the crater, and that shows you that that was basically due to the seismic wave that was passing through it as it cooled off. Then you get down to peak ring basins. Here we're talking about, so the example of the complex crater, you're talking about tens of kilometers in size. So that's the Euler crater at 28 kilometers. The Schrodinger crater is a great example of a peak ring basin. Here, instead of it rebounding to a point, it actually rebounds into a ring that propagates outward. And then as it was propagating outward, the surface froze. And so now you can kind of have this multi-ring or two-ring shape within the basin. And then a multi-ring basin, here you have Oriental, a crater in Mare Orientale, and that is roughly around 1,000 or 970 kilometers. And now we're getting to hundreds of kilometers or even low thousands of kilometers. You're starting to see basically such a massive event that the seismic waves which propagated through this were large, and the surface was molten enough that you can see multiple wave troughs or multiple wave peaks as it propagated outward before it froze over and froze in time. So you can really kind of get an understanding of just the power that goes into these particular phenomena or impact cratering. On Mars is a little bit different than the Earth, in that Mars does actually have erosion, but not nearly as much as the Earth does. And so what we see is a lot of simple craters or standard craters, and we also see eroded craters, something we don't really see here, or at least do not see very well here. And the reason for this is craters on the Earth are eroded via both water and wind, whereas eroded craters on Mars are mostly eroded due to subsurface water. So there's a great deal of subsurface water underneath or on Mars. Actually, I'm hoping to get permission to put a talk that I just sat through. Where am I going with this? I'm a part of the Northern Virginia Astronomy Club. We just had our meeting, and the speaker was a great speaker who talked about basically water in the universe. And one of the things that he highlighted was the substantial amount of water, liquid water, that lies underneath the Martian surface. So occasionally what will happen is that the surface will get sufficiently hot that the heat will penetrate down to the water level. I should say, sorry, a substantial amount of ice water underneath the surface. But at some points, the heat or the surface may get hot enough that subsurface ice may in fact melt and essentially turn the surface into kind of muddy. And so you have these kind of eroded features which have that kind of look like mudslides. And then you have you can also have impacts into icy regions. So the impactor doesn't quite hit into stone; it actually hits into a substantial amount of ice, and that causes a much stranger sort of seismic pattern of debris as it comes out, because of the fact that it's the secondary effects, or the secondary stuff, or that technical term, they get blown out, is mostly muddy water. This is an example of the kinds of craters that you would expect on the Earth. So here is an example of what we would call a multi-ring basin or what would I call it? Not a multi-ring, a peak ring basin on Mercury or the moon. This is CHICXULUB, which is a crater which is both half on and half on the land of the Yucatan Peninsula. We believe that this crater is 180 kilometers in size. When it was fully formed, when it was initially formed, we believe it was anywhere between 10 to 30 kilometers deep. Right now, this is not the scale. Basically the crater wall lip is only, I think it's like at highest 3 meters an extent. So these crater walls are not very obvious whatsoever. You actually need very precise instruments to see the effect on the change in the topography for the crater rings. But anyway, when they formed, it was the crater was 10 to 30 kilometers deep. The impact, we believe, was about 10 kilometers in size or so, and this was anywhere between 65 to 68 million years ago. This is what caused the last mass extinction, or the fifth mass extinction, which used to be known as the KT event. It's now known as something else, some other, because they've changed the eras, the names of the eras. But essentially, this is what killed off the dinosaurs. This impact, the reason why the dinosaurs died is because a 10-kilometer rock smashed into the earth roughly where the Yucatan Peninsula is, and it really what it did, the reason why it was a mass extinction, was that the material from this impact got blown out to the point that it didn't just fall back onto the earth. It actually mixed into the atmosphere and hung in the atmosphere for a considerably long time. And it caused, in other terms, a nuclear winter. It blocked out the sun. It changed the chemical composition of the atmosphere. It was more carbon. There was more carbon dioxide, less oxygen per unit volume. And so things, well, they just froze and suffocated to death for the most part. I don't think it was the Death Star that did this, because I would think that if the Death Star did this, they would have done a much better job. They would have, annihilated the entire planet. But maybe it was a test run. Who knows? Now here's the fun part. Here's the really cheery part of this lecture. This is a plot of impactor size across the top. Across the top. On the bottom is the impactor size, is the crater size. On the tippy top is the equivalent amount of energy or tons of TNT that will get released. The tons of TNT amount of energy that results from the explosion of that impact. And then on the y-axis is how frequently this happens. Now, you may have heard of an event called Tunguska, which was an impact event in Siberia, in the Tunguska region of Siberia, in around 1905, 1910, somewhere in there. That was an explosion that was heard for hundreds of kilometers away. That was very interesting in the sense that the evidence that we have of it, when folks went to investigate and took pictures of the site, they didn't find a crater. They found all of the trees blasted flat. So what we believe is that as the impactor came down, it's going to heat continually as it moves to the atmosphere until even that the atmospheric friction can cause it to explode. And so we believe that the impactor came down, actually did not hit the earth, but exploded over the surface and caused that flattening, that devastation underneath it. Only about a few years ago, there was another impact, again, a fireball that blew up in the atmosphere that shattered glass for many kilometers. That actually injured about 1,000 people. Probably the injuries weren't all that major, but we're talking cut glass and a little bit of debris from the explosion. But what we can see here is, when we think about, silly movies like Don't Look Up or whatever, or Armageddon or what have you, we think of the Earth killers, the ones that are going to destroy all life on the Earth. Well, that only really happens every 100 million years or so. So give or take, we're kind of due for that, because the last one happened about 68 million years ago. So we're kind of getting into the range of maybe we should look for the next Earth killer. But really, what should we should be looking at are those that are coming every millennia or every million years, and these are going to ruin the lives of a lot of people. They won't mess up the Earth as a whole entirely, but they will cause countrywide devastations. They will cause, some may even cause continent-wide devastation. We're talking the loss of millions, if not billions of lives. We can still have an Earth and we can still have a livable biosphere, but there are comets or asteroids, impactors, which have a frequency of millions of years that can do massive amounts of devastation. And we haven't really seen evidence of that. So we are definitely overdue for a massive impact. And we really don't have a great way of dealing with it. So sleep tight. I mean, we've got the DART mission. So far, the best that we got is, if we see something coming at us, is to launch a mass of something at it, and try and knock it out of the way. That's really the best we've got. Unless, of course, Trump is president, then he will order it to be nuked, but which will not do really much of anything. But that's neither here nor there. So let's have a little bit of fun. Share screen. Let's go with that. So I'm going to put that over here. So there's a website that I like that sometimes I just play with whenever, I am having a rough day. I put it in the chat. Yes, and there is always cat videos, which I also watch with frequency. So what you can do is you have three options. You can choose the Earth, the Moon, and the Mars. And like I said, almost always choose the Earth. Once you choose the Earth, you now have a few options to play with. You can do the projectile diameter. That's the size of your impactor. So it goes from roughly 100. The smallest impactor you can create is 100 meters in size, all the way up to 15 kilometers in size. So CHICXULUB was, I believe I said, was about yay big. I believe it was 10 kilometers in size, roughly speaking. And Barringer crater was much less than 100. So you can choose the diameters. You can choose the projectile diameter. That basically helps inform the mass. Not sure I like the term overdue. There is no mechanism for, yeah. I see what you're saying. I don't really know how best to, I don't know a better way of phrasing it exactly. From a statistical point of view, we really haven't been hit by a once in any crater or any impactors that have a frequency of more than once per 100,000 years. We really have not seen any strong evidence for it. So, I don't know. I will freely admit that I'm crap at statistics, but my sense is that the probability of us being impacted by one is getting larger as time goes on. Maybe that's a bad way of thinking about it. But getting back to this, so you can choose the diameter size. You can also choose the trajectory angle, which is basically how inclined to the surface it's going to hit. So 90 degrees would be a straight down hit. And then, 8 degrees, 10 degrees would be an oblique hit where it came in from the side and then smashed in. Along those lines, you might wonder why it is that craters seem almost exclusively circular. There are some examples of oblong craters, particularly on Mars. But almost entirely, if you look at the moon, you look at Mercury or what have you, or any other cratered surface, an asteroid or moon, the craters are all circular. So naively, you would think if you have something coming in an oblique angle, it's going to smack and it should make the thing oblong. It should basically carve out part of the Earth, very much like a divot from a golf club. But again, you have to remember that the crater itself is not caused by a digging action. It's caused by an explosion. So as this thing hits, it will affect the geometry to a certain extent, but the main mechanism for the geometry of the crater itself is due to the explosion, which is roughly spherically symmetric, which is why all craters, or almost all craters, are circular in shape. So you can choose a trajectory angle. I'm going to set it at 45 because law averages, that's the angle that it's going to come in. Although, we'll just put it at 45. And then you can do the projectile trajectory. And you can put it up to, I like to put it at 40 kilometers per second because, again, that's about average. You can then figure out what your projectile is made out of. Your options are ice, porous rock, dense rock, or iron. Going from low density impactor to high density impactor, you can think of this as a comet, a S-type asteroid, or a C-type asteroid, an S-type asteroid, and then a metallic asteroid. I'm going to go with an iron. And then you can figure out what happens if you smash it into. You're getting ahead of me there, Clive. You can figure out what it is that you can water, sedimentary rock, or igneous rock. Now, obviously, most of the Earth is covered in water, but I believe that most of the habitable surface is actually covered in sedimentary rock. Although I'm sure a geologist will yell at me because I've got it wrong. But let's just put it that way. And then let's just put ourselves 250 kilometers away, and then submit. All right, now let's start off with, let me use my location. My location is Baton Rouge, Louisiana. Where is it? Aha, there is the University of is Louisiana State University. That's the Memorial Park. That is Tiger Stadium. You can choose where you're located. For this demonstration, I am going to target Tiger Stadium. Boom! That is the size of the crater. So this is Baton Rouge, relatively small town in the United States. It has a population of about 100,000 people. So this is essentially the city center and surrounding suburbs, as it were. So almost the entire city is in a crater. The specifics, the crater width is about 1.9 kilometers in size. The crater depth is 409 meters. It would cause an earthquake of about 6 magnitude where we are. But we can also do fun stuff. So that's the crater size. So basically that's where it goes. This is the crater depth, and we'll for you Brits out there, I'll choose Big Bang, or Big Ben rather. So here's the crater. Here's the Big Bang, Big Ben as a reference point. Then we get data, or we get damage. And so no significant damage from the atmospheric blast. So for this impactor, and again, I chose a relatively small impactor, about 100 meters or so, and I chose average values of the trajectory and the impact speed. I did choose a dense object. I did choose iron, but from 250 kilometers away, you wouldn't have people 250 kilometers away really wouldn't have too much to worry about in terms of what's going to in terms of damage that they might expect. You know, Baton Rouge is toast, but New Orleans, on the other hand, I think New Orleans is fine. Let's check. Let's see. New Orleans means to Baton Rouge. That is 81 miles. So yeah, so that's definitely within 250 kilometers. So, oh no, I need to think that. 81 miles, 2 kilometers. That's meters, miles to be 130 kilometers. So let's go back. How would people in Louisiana, or how people if a meteor of this size, of these characteristics, smashed into Baton Rouge, how would that affect people in New Orleans? Again, no significant damage. Basically, that they would be fine. Now, for the next example, let's go back. Let's have some fun with it. Let's choose a 5,000 meter, roughly. We should do the same. Let's choose a 5,000 meter projectile. Same characteristics. And actually, let me check something. All right. Let me see if I can. This is for the Brits. So it tells me that Exeter, which is where I think a certain individual is located, is 280 kilometers away from London. So let's move that 280. So what would happen if that happened? What would happen if a 5 kilometer rock, 5 kilometer bit of iron smashed into Exeter, UK? How would people in London feel about it? Well, that seems to be the city of Exeter, or town of Exeter, or however you want to call it. I don't know if you can see that very well. Let me do this. Haha. So there it is. Boom. So that's the size of the crater that would happen. Not really overly familiar with topography or locations in the UK. I believe London is over here somewhere. But yeah, that's the size of the crater that would happen for a 5 5-kilometer chunk of iron smashing into the surface. Now, the crater size would be 66 kilometers across in diameter and would be 1 kilometer deep. So if we again compared it to Big Ben, barely noticeable. To get that French action in there, that would be the Eiffel Tower. And that would be the Dubai Tower. So it's almost a Dubai Tower size and depth. So that's essentially what would happen. And London, on London, basically everyone would be dead. At that point, the fireball, the temperature in London would be so high that clothing would ignite. Most of the body would suffer 30-degree burns. Paper, trees, grass, those would all melt or burn. Buildings would all collapse. All bridges would fall down. 90% of trees would get blown over and set on fire. So, dogs and cats living together, mass hysteria, mass death. It would be utter destruction. So if someone decided to smite somebody, if the universe decided to smite anybody in Exeter, UK, with a 5-kilometer chunk of iron, then the UK is and probably a good deal of France is kind of not having a good day. That's an excellent question. Would a 5-kilometer chunk of iron disturb our orbit? I don't think it would be appreciably. It wouldn't be appreciable. So if we look over here, the mass for this the mass of this projectile would be roughly 5 times 10 to the 14th kilograms, which seems like a really big number. And obviously, it's done a lot of damage. But the Earth is something on the effect of 6 times 10 to the 24th kilograms. So the Earth is 10 orders of magnitude larger than this impactor. So in terms of the Earth feeling it, no, not so much. I would not expect it to have any appreciable effect on our orbit. And just for completeness, go back. Let's do, that'll work. And actually, let's make this dense rock rather than iron. So it's more like so this would be more akin to the CHICXULUB, the thing that killed off the dinosaurs. There. Now, there it is. Helsinki. Yeah, whatever. So that apparently is Helsinki. And so let's just put it somewhere in the middle. Boom! Helsinki completely destroyed, completely wiped off the map. That's the size of the crater in relation to Finland and basically Scandinavia. So that's the size of the impactor. And so what we do, what we're looking at, so here the crater size will be roughly 90 kilometers in diameter. Again, the crater depth is only about 1.1 kilometers. So roughly, again, the size of the Dubai, maybe a little bit deeper of the Dubai Tower. When we look at the data, even if you're 500 kilometers away, which, I don't know, Judy, you can tell us, is there a major metropolitan area 500 kilometers away from Helsinki? Even there, let's see if I can find something. Okay, so Oslo to Helsinki is 1,000 kilometers. So half that looks like Uppsala or Stockholm. Actually, I think Stockholm would be great. So, roughly speaking, if Helsinki were to be destroyed via a dinosaur killing dinosaur killing impact, everything in Stockholm would essentially also be vaporized. And you can see here, this is actually, according to this is actually not very common. This particular impact could happen once every 370 million years. Impact energies, so forth and so on. Firewall radius 215 kilometers. So you live in Vasa. All right, go back. Let's not be as cruel. Let's say it is a kilometer in size. And how far away are you from Helsinki? I'm just going to put it at 200 kilometers. Submit. Two A's, Rob. There we go. Huh. On the coast. Okay. Well, I won't ask you for your street address, but boom. I think your house would be destroyed. Pretty much it would be inside the crater. So the crater here is, again, this is 1,000 is a crater or a meteor that is a kilometer in size, that is made up of dense rock, not iron, but dense rock. If we look at the crater depth and compare it to the Eiffel Tower, it's roughly twice the size or twice the depth of the Eiffel Tower's height. Then if we look at the data view, if you were 200 kilometers away from Vasa, your clothes would ignite, body would be you would basically be burnt to death. Flammables would definitely ignite. Multi-story wall buildings would be collapsed. Glass would shatter. 90% of the trees, but apparently the bridges would survive. You would have the bridges and sort of major infrastructure would still be intact. 200 kilometers away from Vasa, if this were to happen. And this could happen once every 1.8 million years. So this is what I'm talking about in terms of an impact, that this is not something that should be taken overly lightly. And this is the reason why Mars did the DART mission, is that, again, we don't really see evidence of an impact like this happening within the last 2 million years. So from a statistical perspective, again, I may be thinking of this wrongly, but in my mind, the longer we go without one of these happening, the more likely it is going to happen, because the universe or the solar system is still filled with debris. There are still millions of asteroids and comets and smaller bodies out there. So it's not like the solar system has somehow run out of ammunition to throw at us. There's still plenty of stuff out there. And while the vast majority of it may not kill us in terms of the Earth, it could do a serious amount of damage to a very large chunk of the planet. And again, I'm not even sure what this would do in terms of atmospheric effects, which is really what defines a extinction event in terms of an impact, is how much of that debris is going to be expelled into the atmosphere, and how long is that debris going to be suspended in that atmosphere, causing cooling. Yeah, I agree. I wouldn't be surprised if someone's already done that. If someone hasn't already taken the video and had screaming people over on top of it. Actually, Clive, I'm going to look for that. After later tonight, I am going to look for the sound of screaming people dying on the DART mission, because I think that would be hilarious. Oh, you don't live in Connecticut. I see. All right. I think at this point we're at 55 minutes. So at this point, I will continue on with talking about volcanism and all the rest next time. Actually, when I was creating this this slide deck, this is where I'd actually split it up the lecture into two parts. So this is where I normally would stop with this lecture. So as always, I hope you found this educational and entertaining. You learned something. If you like this content, please like, share, and subscribe. Hit that bell for notifications. And if you would like to help us out here at the observatory in our outreach efforts, please consider becoming a patron or just hitting me up on PayPal. All proceeds go to improving the observatory or for improving the student club here. So I will, as always, hang out a couple more moments to see if anyone has any questions. And if not, then I will bid you all adieu. Oh, I will say my intent, while you guys might be thinking up some questions, I do have still a lot on my plate for today, but one of the things that I would like to do is I have a couple of new toys for the office, like a lavalier mic. And so I want to try another attempt at doing a lecture at the board. This lecture would be less mathy, I guess, and more an attempt to try to convince you that up, down, left, right really aren't things. They are arbitrary. That basically direction is what you make of it. And so I want to do that. So I might do that later. I might go live later tonight. Who knows? I don't know. Like I said, I've got a lot on my plate today. So how am I feeling today? If I were to be honest, not great, but you know, it is what it is. How are you feeling today, Nimrod? All right. Like I said, thank you all for being here. Clive, Judy, Chris, Nimrod. Who did I miss? Did I miss anyone else? Chris, Bellywood. Yeah, I think that's everyone. Thank you again. Thank you all for being here live. And thank you all, whoever watches this later in time. Again, I hope you found it useful and entertaining. So, yeah, Nimrod, I understand. I get you. All right, folks, have a good one. Clear skies. Peace out, and I'll see you on the next time.